Okay, so we are almost at the end of our syllabus, what I would like to cover in this course, and I guess only 2 more classes we will be having. So today is one where we will start the this introduction on the MOSFETs, the metal oxide semiconductors, and what we have to learn here is the basic operation, how they are working, the working principle, and how they are employed in circuits. So these are the 2 things that we are learning for each of the devices. So we are learning the operating principle and the working principle and how they are used in various electronic circuits. Now the good thing about MOSFETs are that they are almost never used as amplifiers. They are used as switches, and so the switch operation is already we are quite familiar with. We have to make the device operate in either saturated condition or in cutoff condition. So that is all. So that's why you will see that there is not much to be discussed when it comes to the electronic circuits for this MOSFETs. And also these MOSFET switches are almost entirely used for digital switches, not even analog switches. So in analog switches there was a situation where you have to understand or study the AC equivalent circuit, because there is some AC signal flowing through it. So AC equivalent circuit one has to know, but here in MOSFET that is also very simple. There is because it is almost entirely used as digital switches, and as we know that the switch, even if it is an equivalent circuit, the equivalent circuit of a switch is always the same. It is a simply ideal switch along with a resistance, some resistance which is very small in magnitude. So you will see that when we cover, we will come across these things again. But the main thing in MOSFET is to understand how it is actually working, the working principle of the MOSFET. So in MOSFET there are 2 types of MOSFETs. One is depletion type, another is enhancement type. So first we look at depletion type MOSFETs. So in depletion type MOSFET, we have one semiconductor, N-type semiconductor, and as in FET we are having two regions of P-type material in the middle, right? So and between those 2 regions there was a narrow channel. But in depletion type MOSFET we have only a single region of P-type material, as you can see in this diagram, and it is having a very narrow channel at one end of the entire device. Okay, at one side of it there is a very small channel. So this channel is very small. It is drawn in this way because to show it a larger, but it is very small, very narrow channel. Another important thing is this, that the gate, you see the gate lead here is coming to a metal plate, but this is not connected to the, or this is not attached to the semiconductor, N-type semiconductor directly. In junction field effect transistor, JFET, it was directly attached to the P-type material, right? It was directly attached to the P-type material. Here it is not directly attached to the body of the semiconductor, but it is attached to a silicon dioxide layer, and through this it is attached to the semiconductor body. So what is this silicon dioxide doing here? So this silicon dioxide is actually an insulator, it is actually glass. Silicon dioxide is nothing but glass. So glass, as you know, is a very good insulator. So this gate here, whatever voltage you are supplying, there is an insulator between the metallic lead and the semiconductor. So what happens? There is no current passing in this gate channel. There is absolutely, you can consider absolutely zero current passing in this gate terminal. So in JFET also I told you that because it is reverse biased, the junction is reverse biased, gate source junction is reverse biased. That's why there is very little current. Now the presence of an insulator here even diminishes that value to even lesser current. So you can understand that the input impedance in these MOSFETs are even higher. So the distinctive characteristic of a MOSFET is this silicon dioxide layer, metal oxide. Some metal oxide layer is here. Metal is a good conductor, but metal oxides are not good conductors, they are insulators. So the metal oxide acts as an insulator, and that gives rise to all the properties like very high input impedance, zero input current. So these properties are there because of this metal oxide layer which is there between the gate and the semiconductor. Now this particular semiconductor. Now if you come here in the semiconductor, how the doping has been made, the N region and the P region, this gives rise to the depletion type. The depletion type MOSFET looks like this. There is another type which I already told you about, enhancement type. Enhancement type, this inside of the semiconductor block will look different, but the metal oxide layer, silicon dioxide layer, will still be there between the gate and the semiconductor. So it is still a MOSFET, but its type will be changed because of the doping arrangement, because of the difference in the doping situation. So in the depletion type, the doping is like this, that you can see in the diagram. There is only a P region at one end, and now you can see that this P region is called a substrate, and there is a lead coming out of that substrate, and so there are actually 4 terminals in this device. However, the substrate and the source are sorted, are connected together. So it is a 3-terminal device at the end of the day. At the end of the day, you need to supply 3 different potentials at these 3 different points. Substrate is connected to the source, so they are together, they are connected. So it becomes a 3-terminal device. Now let us come to the operation of the depletion type MOSFET. D-MOSFET it is usually called as. So what would be the operation? As we know that what is controlling the flow of current through this semiconductor between source and drain is the gate source voltage. Here also the same thing is going to be applied, and we have to understand how the control of the current is taking place. Now you can very well understand that if we don't have a gate source here, if we just have a drain source voltage, the current will flow through this narrow channel here, and it will establish some current. Now if you are applying a gate source voltage on top of it, what it will do, as you know, if it is a negative gate voltage, then what it will do, it will actually narrow down this channel, as we saw earlier in JFET also, this causes the narrowing down of the channel. So why this happens here, you can see that if the gate is negative, the source is positive, then this substrate is connected to the source, so the substrate is also positive. So the holes here are getting pushed further away from this side. So this is getting pushed means this is trying to enter in this region, in this narrow region. So whatever carriers, majority carriers, N-type carriers were there, they are getting combined with the P-type holes. So this region from where the electrons will, this narrow region is getting narrower. That is what I try to say. So this narrow region is getting narrower. And the depletion here happens from this side, from the side of the P block. So the P block, as if it extends out in a depletion layer. Remember that in the depletion layer there is no carriers. Okay, in the depletion layer there is no carriers, but the depletion layer is formed due to combination of P-type and N-type carriers, due to combination of holes and electrons. So how this combination happens? Because the source is positive, the substrate is positive, so the holes are getting pushed away in this side, so the depletion layer increases. And as we know, if we keep on increasing the gate source voltage in a negative manner, then at some point this will be completely blocked. This channel will be completely blocked, and that would be the cutoff voltage. So it acts exactly like the JFET. It acts exactly like the junction field effect transistor when your VGS is negative. That means gate voltage is negative than the source voltage. So when VGS is negative, less than 0, it works same as the JFET. So if you draw the output characteristic curve, you will find that the same output characteristic curves as in JFET are appearing. The transconductance curve from VGS cutoff to VGS equals to 0 looks like the same. It is like a exponential, it is like a square law. In the following the square law, it is increasing. But what is the speciality of the D-MOSFET? How it would be different than from the GFET? So we have made some difference in the arrangement and the construction, at least to bring about some new functionality. That new functionality is that the D-MOSFET can also be operated with gate source voltage being positive, gate source voltage more than 0. In JFET, remember that gate source voltage, the maximum gate source voltage was 0 only. It could not be more than 0. But here it is allowed to have gate source voltage more than 0. Why in JFET we cannot have VGS greater than 0? Because that would make the gate source junction forward biased, and then it would act as a diode, and the entire property of Ig equals to 0 will be lost. So we don't work the JFET with positive VGS. But here, even if you make the VGS positive, will you get a gate current? No, you will not get a gate current because of this because of this insulator layer. This insulator layer prevents any current in the gate circuit. That's the reason why we can experiment now with applying positive gate source voltage also, and see what happens. Let us see what happens when gate source voltage is positive. Gate source voltage positive means you can consider that a positive potential is at the gate and the negative potential at the source. So what will happen? the electrons at the source, you will be supplying more electrons here in the n type, as well as there would be combination of electrons and holes at this end of the p type material near the substrate lead. So when this is getting combined, so the holes from this side is trying to come here, come to this side, getting attracted to this substrate lead. The holes from the p type from the p area is getting attracted to this substrate lead. So as they are trying to flow here in this narrow region which was there for the flow of the electrons, this also expands, this increases, this narrow region increases. So it allows for more flow of current. That means if you make gate source voltage positive, then you will have more current flowing when compared to the current when gate source voltage is 0. And fortunately for us, the current in the positive region of VGS as well as in the negative region of VGS follows the same square law that we studied for the JFET. So we don't have to study anything new, we just have to understand the working principle, and the same square law is applicable to get the drain current with respect to the drain source current when VGS is short circuited. This parameter is what we need only. So, and this parameter is given to us by the manufacturer. They calculate the drain current by making VGS equals to 0. They calculate the drain current and give this value. Any other current when VGS is not equals to 0 can be obtained using this relationship, and this is the square law relationship. VGS off is the VGS cutoff. There is a negative voltage beyond which if we go, there is no more current. So when you see VGS equals to VGS off, current becomes 0. So but when VGS is more than 0, then also you will get some current ID which will be more than IDSS. This is what is important here. Previously you see that VGS and VGS off were both negative, so the signs were getting cancelled. But when VGS is greater than 0, VGS off is less than 0, some negative value, suppose -4, and VGS is +1, then you will have 1 minus 1 by -4, that is 1 plus 1 by 4. So this value becomes more than 1. So ID is now more than IDSS. And the same square law is following. That means the transconductance curve simply extends in the positive VGS region. So now you see the curves. You see the transconductance curve here is simply extending in the VGS greater than 0 region. And the output characteristics you see here, previously for JFET it was limited till VGS equals to 0, till this curve. But now we can have +1, +2 like this. We can have more curves here. And some load line, whatever load line is you are having due to the arrangement of the network elements, that can intersect any of this curve, whichever VGS you have selected, that will decide the Q point now. Now, so please remember that the Depletion type MOSFET has two modes of operation. One is when VGS is less than 0, another is when VGS is greater than 0. These modes of operation are depletion mode and enhancement mode. So the depletion type MOSFET has the depletion mode as well as the enhancement mode. Why these are called like this? Please understand, depletion mode, we are increasing the depletion layer. That's why the depletion mode. Enhancement mode, because we are enhancing this channel, this current, the path for the electrons to flow, we are enhancing that. That is why it is enhancement mode. Why this is called depletion type MOSFET, that we will discuss when we just come to the enhancement type MOSFET. Then you will be able to understand the difference. So there are two words, depletion and enhancement. There are two types of MOSFET, depletion type and enhancement type. The depletion type MOSFET works in two modes. There also a depletion and enhancement. So don't be confused here, try to distinguish these things a bit carefully. Enhancement type MOSFET does not have two modes of operation, it only has the enhancement mode of operation. So there is no further distinction there. Just see the symbols, look at the symbols. When we are having VGS less than 0, then your arrow is like pointing inwards. This arrow is pointing inwards. And when you have VGS greater than 0, this arrow is pointing outwards. Okay. So please keep this in mind. So this is distinguishing your VGS less than 0 and VGS greater than 0 symbols here. And these are joined. You see the substrate and the source is joined. Okay, so these are joined. So there is like the JFET, if you remember, the JFET did not have any enhancement mode. It was only in depletion mode, right? It was only having this part of the card. So if we had set VGS equals to 0, then it would go to the saturation region directly. It would go to the saturation region. VGS equals to 0. That is the curve here. So normally for setting in the saturation region, we used VGS equals to 0. But now the D-MOSFET can be set with the Q point as VGS equals to 0 and still can be used as an amplifier. Why so? As you can see, this curve is extending this way. So if you supply some AC signal at VGS equals to 0, then this AC signal comes out as a AC current ID with some degree of enhancement, which is given by the transconductance GM. The same transconductance GM idea is still there. So GM into VGS will be ID, and you can have this relationship still valid at VGS equals to 0, which was not possible for JFETs. So there is a zero bias concept for depletion type MOSFETs. There is a concept of zero bias. Zero bias means I am setting the JFET bias at 0 but still able to maintain an amplification at the still be able to employ this as an amplifier. So you can see how this is getting done. So since we have connected the source to ground, the VGS is 0 because VG will anyway be 0. The voltage at VG would be 0 because there is no current, in no IG current. So VG is 0, Vs is also 0, so VGS is 0. So when VGS is 0, if you apply a AC signal at that in this situation between the G and S terminals, then you will find an output current ID coming out like this, riding over the DC offset current. So this is one biasing for the D-MOSFET. That is only one thing, one biasing we study. If there is any other sort of biasing, like we have already covered in JFET. So if you have a resistance here after the source, then it becomes a self bias, the self bias D-MOSFET. So we already have studied the self bias JFET. In the same way we can analyze the self bias D-MOSFET also. So we have to keep in mind that the D-MOSFET is nothing different from the JFET, only it has an additional enhancement mode. That is a region where we can have VGS greater than 0. Now we come to the enhancement type MOSFET. The enhancement type MOSFET, in construction you can see the difference, very easily you can note the difference. There is no narrow channel appearing anywhere. The entire middle part is the p-type semiconductor. So it is like a bipolar junction transistor, right? There is a two junctions are there, but it is not worked in the same way. Constructionally it is similar, the semiconductor part, but you see the gate is coming here via, or like an insulator is between the gate and the semiconductor. That makes all the difference. That is why it is a MOSFET, because of the insulator. It is a MOSFET because of the metal oxide semiconductor. That is why it is MOSFET. Why it is enhancement type? Because it works based on the principle of enhancement of the current conducting channel. That principle we already discussed in D-MOSFET. So when we have VGS greater than 0, then what will happen? The channel which was already there expands. The channel which was already there expands now, enhances. That's why it is enhancement mode. The enhancement type MOSFET only works in the enhancement mode. It doesn't have a depletion mode because there is nothing to deplete further. It is already blocked. So if you just apply a drain source voltage, you will not get anything here flowing here. The channel is already blocked. So the work of the gate source voltage is to create that channel. The work of the gate source voltage would be to create that current conducting channel, and that can only be created when gate source voltage is greater than 0. When gate source voltage is greater than 0, because only then what would happen? This negative, more negative would potential would be there in source and substrate. So that would draw holes from this region towards this right hand side, from the left to the right, and at the left there would be a region created which is devoid of these holes. So the free electrons, if they are having sufficient push between source and drain, there is a potential developed, the free electrons will find a path to go through from the source to the drain. So here the path is getting enhanced as we are increasing the voltage. That's why it is called enhancement type MOSFET. So the construction makes the type changed from depletion to enhancement. In the depletion type, there were two modes, because the gate source voltage was either negative or positive, and that gave rise to two different modes of operation. In the enhancement type, there is only one mode, which is gate source being greater than 0. Don't have anything else. So we have to have VGS greater than 0. Then only you have a channel created here. And when that channel is created, then the current flowing through it behaves in the same way as per the square law. It will behave. So everything now remains the same. But one important additional parameter comes into picture. A new parameter comes into picture. What is that parameter? That parameter is a voltage called Vgs threshold. Vgs threshold. TH. What is Vgs threshold? So you see that just making Vgs greater than 0 will not create this channel. We need to impress a sufficient amount of positive voltage here. Only after that a channel will get created, and from thereafter the current will follow a square law. So this voltage, before which we are not experiencing any current, any drain current, that voltage is called Vgs threshold. So below Vgs threshold, so Vgs threshold is here like the Vgs cutoff, the cutoff voltage that was there for JFET and D-MOSFET. Here in E-MOSFET it is Vgs threshold. This cutoff voltage in JFET and D-MOSFET was negative. In E-MOSFET it is a positive voltage. So before Vgs TH, you see that there is no ID current. Here also before Vgs TH there is no ID current. After that the current grows as a square law. This is the transconductance curve. So as if the transconductance curve from the left half of this from the left has been shifted to the right. Now after a certain value of this positive voltage, what happens, that there is no more enhancement in this enhancement of the channel. No further enhancement of the channel happens, and after that this channel is simply acting as a constant current source. So some ID set gets developed, and that simply continues after that, after this some amount of voltage. And in this region the semiconductor simply acts as a small resistance. It is an ohmic region now. Small resistance it offers now. So this is the thing. Now you see Yes, this is all that is there. Now yes, the concept of hard saturation. Now E-MOSFETs are almost entirely used in digital electronic circuits as digital switches. So digital switches means either it is having a high VGS or it is having VGS equals to 0. So as soon as VGS equals to 0, you can understand it is completely cut off. No ID, no current will flow through this device. When VGS is sufficiently high than VGS TH, then what happens? Your current saturates. There is a constant current now in this part. It is in the ohmic region. So this behaves as a switch, as a closed switch in that case. So this hard saturation is very simple to be established, and this is given by the manufacturer that what your VGS on, there is a parameter VGS on that you need to set in order to make it behave as a closed switch. So VGS on is given by the manufacturer. So it is worked only in these two modes, only in these two voltages. One is VGS on and another is VGS equals to 0 or a very low voltage. And in this such case, you are actually getting a either a closed switch or a open switch from the E-MOSFET. These are the symbols. Just note the symbols here, that you are having this okay, here actually these symbols are for either NPN or PNP. So both types can be there. So this is NPN and this is PNP. These are the symbols. One important aspect of MOSFETs is that there is a maximum gate source voltage. There is a limit to where you can take the gate source voltage to. So as you had noticed that in both the D-MOSFET and E-MOSFET, we can have a region where VGS is greater than 0. But can we make it as large as possible? No, we cannot, because there is an insulating layer at the gate, and as we all know that the insulation can only withstand a voltage or an electric field across it up to a certain extent. Beyond that, the insulation will break, and when the insulation breaks, the entire operation gets destroyed because we have a high Ig current. So we must ensure that we are not destroying the insulation. So we have to ensure that we are supplying only voltages which are less than this maximum gate source voltage, and this VGS max is specified by the manufacturer in the data sheet. Now you can destroy the insulating layer not just supplying a high VGS, but in many other ways you will be able to destroy the insulating layer. How? If you insert a MOSFET in an already powered up circuit. So the circuit is already powered up and you are inserting the MOSFET there, then there will be high transients happening at the junction, and that can easily cross the VGS max. VGS max is very low actually, it is maybe 20-25 volts like that. So it is very important. So when we will be doing the experiments in the lab with MOSFETs, particularly with MOSFETs, with any other electronic devices also it is true, but particularly with MOSFETs, they are very sensitive to this thing. So you destroy the MOSFET if you insert it in a powered up circuit. Also, you have to be very careful while handling the MOSFET, because our bodies are having a lot of static electricity, and 25 volts of static electricity can easily flow if we are touching the MOSFET with our bare hands before grounding ourselves. So it is very important that we ground ourselves while handling MOSFETs and such sensitive electronic equipment. So in our own labs, electrical laboratories, how you discharge yourself? You discharge yourself by touching the body of any apparatus which is having a ground wire. You know that the ground wire of any apparatus is connected to the body of that apparatus. So you can also touch the body of the apparatus to discharge any static charge you might be having on your body. Only after that you should touch a MOSFET, and you should be very careful that you are not inserting a MOSFET in a powered up circuit. And this is exactly how many of our students are wasting their time by damaging their MOSFETs and then not able to get any results during the laboratory experiments. So we all experience this while working with the students. So some batches are sitting not getting results, and finally they found that the MOSFET is not working. However, when they were supplied the MOSFETs come in ICs, actually in integrated chips. So these chips, when they were given the chips, they were in perfectly good condition. So they had damaged it because of their careless handling, and that results in their own time getting wasted. They are not able to finish the experiment. So please keep this in mind whenever you are here in the IIT and start working in the laboratories, especially in electronic laboratory. It is very important that you ground yourself and you never insert any device in a circuit which is powered up. So to avoid such accidents, sometimes their manufacturer builds a Zener diode in parallel to the gate source of the MOSFET, which has a Zener voltage rating less than the Vgs max. It obviously gives protection, because what happens if the gate source of this Zener diode starts conducting whenever there is a high transient happening at the gate source junction. The Zener diode starts conducting and it limits the gate source voltage to something less than Vgs max. So it does not increase beyond Vgs max. This gives a protection, that is true, but it also reduces the high input impedance, because there is some current because of this Zener current. There is some current in the gate source circuit. So it reduces the high input impedance. Sometimes it is beneficial if there are MOSFETs available with the Zener diode, there are MOSFETs available without the Zener diode. If your application does not need a very high input impedance, then to give protection to that circuit, to the network, the Zener diode, you can use a MOSFET with the Zener diode protection in there. Otherwise, you have to be very careful yourself in order to handle the Zener diodes. So I will end this today's lecture here only, and we have a very small part left in the syllabus, and I think we can cover it in the next lecture only. So if I am able to do that, the next lecture will be the last lecture, but the tutorials will continue and I will plan the tutorials accordingly. There I know that the tutorials are also quite following up the lectures, but till we are having the session classes, I will also plan some tutorials so that you have more practice of the numerical problems associated with this course. Okay, so here I will end the lecture now. Is there any doubts, any question? So please understand the difference between the D-MOSFET and E-MOSFET. The difference is in the construction, and that leads to the functional difference. D-MOSFET has two modes of operation. E-MOSFET has only one mode of operation. And how the modes are getting established due to the Vgs value, that you need to understand. Okay, thank you for your attention. So I will end the session today. Thank you.